the main thing that I learned from analyzing these images from Planck is just how amazingly, in some ways, how amazingly simple the universe is. So we're actually observing light that has been traveling since the universe was just a few 100,000 years old, and the universe was much simpler back then, simple enough that we can actually make predictions for what it should look like. And we do that by using things we've learned about the world from experiments here on Earth. And for example, one thing we've learned is that atoms that are 14 billion light years away, you couldn't be any further away, and we'd still see them. Atoms really far away are just like atoms here on Earth. So how matter behaves here is exactly the same throughout the whole universe that we can observe. And that in itself is a pretty amazing fact. The universe used to be just about the same everywhere. So there's just as much stuff in this part of the universe as in this part of the universe. And there were just tiny differences in how much matter there was, say, here versus here, to less than 1% variation in how much stuff in one region versus another. And over time, gravity has increased that. So if this region had more mass, it would gravitationally pull matter in from this region, and then be even more massive, and so pull even more stuff in. And through that process, these really small differences from complete uniformity grew to be the universe we see today. Without these small departures from complete uniformity, we wouldn't have any galaxies, any stars, any planets, or any of us. So we're looking at a time when we can see these initial irregularities, and that are without which we wouldn't exist, and it gives us an opportunity to study our origins. And what we're finding is that the picture we have is all consistent with this story of how these density fluctuations were created during this when the universe was mostly composed of this very exotic form of matter that was causing the expansion of the universe to accelerate. A lot of the models of inflation, that's this exotic material that was causing the universe expansion to accelerate early on, a lot of the models of inflation model this as arising due to something we call a scalar field. And until the discovery of the Higgs, we didn't have any examples of scalar fields in nature. So the Higgs is an excitation of a scalar field, and so it's in that way is very indirect support for trying to use a scalar field to model what's happening in the very early universe. Some people speculate that the Higgs field may actually be this inflation field, and maybe that's the case, but it's a big leap and highly speculative, and we just don't know right now. One of the mysteries of the universe is that most of the matter in the universe is well, it's something we don't know what it is. It doesn't interact with what we're made out of. It doesn't, not very strongly with atoms, and we call it dark matter. It's flowing through us right now, and we'd love to know what the dark matter is. And there's many efforts to actually detect dark matter, and here at CERN we're hoping that actually dark matter gets produced in the laboratory. So one of the things we know from laboratories here on Earth, and we've known for a century, is that matter on very small scales, on the scale of atoms, behaves very strangely, quite differently from how we observe things on large scales. And matter is always in motion, and is fluctuating, and we refer to these fluctuations as quantum fluctuations. And we usually don't notice them because we need special equipment to see some of these effects. But one of the leading theories of our origins, of where these small density fluctuations came from, is that they're the result of these quantum mechanical fluctuations. And you might wonder, how do we see such large-scale effects over the whole sky, how could these be these small-scale quantum fluctuations? And that comes from, during this process of inflation, with the universe expanding so rapidly, stuff that's happening on small scales gets stretched out to be very, very, very large-scale fluctuations. And the theories that are predicting what these small-scale, what these large-scale fluctuations should look like have been very successful in explaining the Planck data. So many of you have heard that this expression, I think from Carl Sagan, that we are star stuff, because we're made out of the elements that were produced in stars. But another truth is that at least this provides a good explanation for the Planck data and for the origin of structure in the universe and ourselves, is that we are amplified quantum fluctuations.